Hi, I'm going to present our empirical evaluation of calibration and long-term carryover effects of reverberation on egocentric auditory depth perception in VR. Distance perception in IVEs is very crucial when users need to react accurately to some special information, like driving to an assigned location or when distinguishing targets in visualizations. However, there's a well-known distance perception problem in VR, the distance compression. Users tend to underestimate the distance between themselves and the object. Although HMDs have improved over the years, allowing for more accurate estimation of depth, the distance compression issue continues to persist and is yet to be completely resolved. So under this circumstance, how can we enhance users' VR experience by improving their distance perception? Distance perception involves multisensory experiences. When perceiving distances in the real world, people may integrate information from multiple perception channels towards estimating overall distance. Auditory depth perception in VR is seldom discussed. VR users mainly rely on visual information. However, with modern IVEs increasingly featuring multisensory experiences, auditory information provides another way to enhance distance perception. In our study, we are using reverberation cue as an information for participants to perceive distances. So what is reverberation? It is the accumulation of sound waves in a space and is created by sound reflecting off the surfaces in the environment. It is resulted in better distance estimation in VR in previous research, and it is shown in addition to visual information compensated for depth compression in VR. Here I want to talk about another important idea in our study, attunement and calibration. Attunement is an important type of differentiation where the human learns to detect different sources of perceptual information. Along with the attunement, the user also becomes calibrated during perception learning. There have been many works have investigated calibration and carryover effects, but they are largely been limited to visual information. So in our work, we aim to discover if users can calibrate their distance perception with reverberation stimuli in VR, and whether this can be used to make users potentially perceive distances to objects more accurately. There are many related work use auditory information to enhance distance perception. Like visual distance perception is influenced by the auditory environmental context through reverberation-related cues, or users tend to associate longer RTs with further distances, indicate the potential to alter RT towards compensating distance automation in VR. Or perception learning via calibration and its carryover effect, like VE users calibrated distance compression when different perturbations of perceptual haptic feedback were presented. Our research questions in our study is to answer whether participants can calibrate to auditory reverberation towards enhancing egocentric distance estimation, and whether the effects of calibration carry over a period of 1 month and 6 months. Our experiment consists of a pretest phase, a calibration phase, and a post-test phase. In both the pretest and post-test phases, participants provide their judgment to the perceived distance of a sound source location without any feedback. So here's a video. So here's the calibration phase video. Participants received feedback and were allowed to adjust their depth judgment to the actual distance of the sound source location within VR. We use within subject in our study, and the factor is actual distance, measure is perceived distance. We use the same audio clip and generated with 10 different reverberation time, and other audio properties remain the same, like intensity. And to avoid the participants simply memorize the stimulus for each actual distance, we separate these audio stimuli into 2 groups, and its corresponding RT were different in the calibration and other phases. The exact ideal RT in the virtual scene should be 0.7 seconds. The RTs of our stimuli are rather exaggerated in effort to study if participants can distinguish sounds more easily and to amplifying the power of the experiment. In order to evaluate the significant interaction effects between actual distance and different phases, the continuous independent variables of actual distance was mean-centered to eliminate any multi-collinearity effects, and the interaction terms actual distance multiplied phase was added to the model in a hierarchical multiple regression, and also predictors actual distance, phase, and actual distance by phase interaction term were all significant predictors of perceived distance. Let's take a closer look of this plot. The linear regression equations will be shown at the same time. The ideal prediction is represented by the dotted line, which characterizes the vertical judgment, the slope of which equals to 1. In other words, the vertical judgment line represents the prediction where participants' perceived distance is equal to the actual distance of the presented stimuli. Thus, a regression line that is closer to the dotted line implies the perceived egocentric distance are more accurate. We can see the regression lines by phase order. Firstly, it is evident the slope of the pretest phase, in which participants estimate the distance without any feedback, is much lower than the other phases. Then the calibration phase that our participant will calibrate it. Then the post-test, we can find that the accuracy is very close to the perfect prediction, and after 1 month, the accuracy drops a little. Then after 6 months, the accuracy still remains better than without any feedback. Let's see distance estimation accuracy in different phases. The accuracy was computed by this formula, and this formula created a sign error of percent accuracy, where negative will represent underestimation of the actual target distance, and the positive values represent overestimation of the actual target distance. The mean percent accuracy scores were subject to a 5-phase multiply 5 trial set repeat measure ANOVA analysis, and it also revealed a significant main effect of phase. And from this chart, we can infer that the participants largely underestimated distance in the pretest phase, while their post-test estimate significantly higher accuracy score even at 1 month and 6 months. So we can say employing a calibration phase appears to improve participants' egocentric distance estimates in IVEs. And our finding that we use reverberation time as information to perceive distance might align with previous work on distance perception learning. Users can successfully calibrate their depth perception based on visual feedback provided during a calibration phase. So what this all mean? We can minimize the need for users to be recalibrated frequently in VR in some applications like training simulation and games. So for our conclusion, users can really differentiate various lengths of artists in VR and enhancing their distance estimation by using perception learning to auditory reverberation. And we find this learning effect seems to persist for at least 6 months. And for our future work, we aim to combine with other types of sensory information and use more realistic reverberation stimuli in our study. Thank you for your concentration on our work. See you in IEEE VR conference.